So first we're going to pull up that simulation. And so here we have a simulation from Phet, as I call it. And we have a fixed volume of gas right now. It can get bigger or smaller, and we don't have any air inside or any gas particles, so we have zero pressure. And I'm just going to use this pump, and I'm going to put some particles in. And this is going to create some pressure. We see our pressure meters going up. What causes pressure inside a closed container with gas in it? Well, molecular collisions. These particles are bouncing off the sides of the container. They're bam, bam, bam. They're bouncing into each other, they're colliding, and they're smashing into the sides of the container. That's creating pressure. The constant collisions with the side of the container. At any one instant, a molecule or particle might not be colliding with the sides of the container, but millions of other ones will be in a real gas. So, or even more than millions, billions, and trillions. There's so many atoms in a bag of gas that it's really unfathomable, uncountable. So there's so many atoms in an actual gas that there's going to be tons and tons of particles always smashing into the sides of a container, even though in a gas particles are very far apart. There's going to be a lot of collisions, so this is creating pressure. And if I increase the temperature of this, what do you think is going to happen to pressure? Well, if we increase the temperature, the particles should move faster. If they move faster, they should hit the sides of the container with faster speed. I think that would create greater pressure. Imagine if somebody threw a softball at you at 10 miles an hour and somebody threw one at you at 60 miles an hour. The 60 mile an hour softball is going to hurt more. There's going to be more force per unit area. There's going to be more pressure. So when you have a fixed volume, a constant volume, if the size of this container doesn't change, adding temperature to it's going to increase the pressure as the particles simply move faster and collide with the size of the container. And I think we reached overload here, so we'll restart that. And same general process happens in reverse. What happens if we cool the particles in a fixed volume of gas? Well, they're going to move slower, and they're not going to probably hit the sides of the container as frequently, and they're not going to hit it as forcefully. So pressure is going to go down. So for a fixed volume of gas, as temperature goes up, pressure goes up. As temperature goes down, pressure goes down. And we'll reset that again. So let's look at another case here. Let's say we want temperature to remain constant, and we're going to actually make this bigger. What's going to happen to the pressure inside this tank? Well, if you think about it, pressure is being caused by the particles colliding with the sides of the container. If it's bigger, the particles are going to have to travel further, and they're going to be spending more time traveling and less time colliding with the actual size of the container. So I believe pressure should reduce, and it is. It's going down. These particles have to travel further back and forth to collide with the size of the container. So when temperature is constant, ignore it if it went up or down. Where temperature is constant, increasing volume decreases pressure. What happens if I push this close together? What happens if I compress this? If I decrease the volume? If I make this smaller? Well, now the particles don't really have anywhere to go. All they're doing is bouncing off each other and bouncing off the sides of the container. This is creating more and more pressure. So when you keep temperature constant, and I know it's changing on this, just ignore that. But if you're keeping temperature constant, decreasing the volume will increase pressure. That's another gas law. And eventually you will reach critical point, kaboom. The hardest one of these to see is what would happen if we wanted pressure to stay the same. If you want pressure to stay the same, what would I have to do if I made this bigger? Well, if I made this bigger right now, you should realize that pressure will go down because the particles have to travel further. So if I want pressure to stay where it is, and I make this bigger, we see that pressure is going down. I'm going to have to apply a little heat to get the pressure back up. So when you have a constant pressure, if we want to maintain constant pressure, as volume goes up, temperature also is going to have to go up. That's just the rule of the game. And again, as volume goes down, if I want to keep the same pressure, We know pressure is increasing as I close this. The particles are getting close together, colliding more. Pressure is going up. So in order to keep pressure the same when you're changing the volume, you actually would have to chill this. So that is a very basic and a very good conceptual understanding of Charles Boyle's and Gay-Lussac's gas laws. And I give you this ranking task. We have 3 different cases. Case 1, Case 2, Case 3, and we're going to rank these, and we'll do them one at a time. We have Case 1. We have 3 containers. All 3 containers are the same exact temperature. So we're going to assume that the speed of the particles inside is the same in each container. So which container is going to create the highest pressure? And we should come up with A, because in container B, which is the biggest, the particles have to travel really far before they collide with the size of the container. There should be lower pressure in there. So A should have the greatest pressure because it's the smallest and the particles don't have to travel as far to collide with the wall. And C is the second smallest, so it would be ACB. B is the largest, particles travel further, and this is actually Boyle's law. As volume goes up, pressure goes down when temperature is constant. And the next one we're going to look at is where we have constant volume. In this case, we're using Gay-Lussac's law. Each container has the same exact size, takes up the same amount of physical space. But one container is hotter than both of the other ones. If the container is hotter, then what happens to the speed of those particles? Those particles are moving faster. In the 200 Celsius container, these particles should be moving much faster. They should be hitting the sides of the container much, much harder. So if we want to rank them in terms of pressure, the higher the temperature, the higher the pressure for a fixed volume of gas. So we have B, C, A in this case. And that's all spelled out there. The particles are moving faster, they have higher temperature, they're generating greater pressure. In the third case, we are now ranking temperature. We're not ranking pressure. Pascal, PA, is a measure of pressure. So each one of these containers has 500 kilopascals. So they are all at the same exact pressure, but they are different sizes. So this is the hardest one of the group. And we're going to rank them. Which one has to have the highest temperature? Well, to me it seems clear that if container A had the highest temperature, there would be much more pressure in here than container B, because if these particles were moving faster than the particles in particle B, there'd be a ton more pressure in there, because not only are they moving faster, but it's a lot smaller than container B. In order for container B to have the same pressure as container A, which is smaller, these particles need to move faster. They need to be moving much faster than container A. So in this case, we have pressure being constant, and we know as temperature goes up, volume goes up. So we are going to need to have this one have the highest temperature. This one can't have. If this one had the highest temperature, there'd be much more pressure in this one than in this one. This one, we can increase the temperature, the particles move faster, but there's so much space, there doesn't necessarily have to be more pressure than this one. So ranking these, again, is B, C, A. Containers have different sizes, and the particles in container A must be moving slower and have a lower temperature than the particles in B or C. Otherwise, it would be a lot more pressure. So that's a conceptual understanding of the 3 gas laws. Mathematical understanding is another slideshow, but hopefully using that Phet simulation and doing this ranking task, you have a better understanding of the relation of volume, temperature, and pressure for gases. This is the phone.